from this lecture onwards, I'll start discussion on diffraction, and just to kind of understand what is diffraction before we get into the diffraction from crystals, this is something that you would have probably done in a physics course, diffraction of optical light through what is called as a diffraction grating. Now imagine that I have these slits, and this is my incident radiation, which let us say is electromagnetic radiation in the visible range. So, we can imagine as follows, that I have a screen out here, I can get what is called as the direct beam, while there are going to be other beams going in different directions. These are what we call are the scattered beams. Now, the scattered beam also will fall on the screen and produce some intensity. Now, the question is whether that intensity is finite or not depends on what is called as the phase difference or the path difference of the rays that are coming out from the various slits in the diffraction grating. So, if I get a finite intensity, I will get another spot which is what we call as a diffraction spot. Now, under what condition, whether a scattered beam will have a finite intensity or not, we can do a calculation of the path difference. So, let us say this is a scattered beam, makes an angle of theta with respect to the direct beam. If I look at these two rays 1 and 2 and want to find out what is the path difference, between let me call this as delta 1 2 to represent the path difference between ray 1 and ray 2. So, let us do the following, and I will put some parameters out here. The distance between the slits is d. Let me drop a perpendicular from ray 1 on to ray 2. Now, this angle we know is theta. Therefore, very clearly this angle will also be theta. And what is the path difference? The path difference, that is the difference between the distance travelled by the two rays before they fall on a detector or on a screen. That this difference is this much, which is delta 1 2. So, clearly from this triangle out here, delta 1 2 would be equal to d sin theta. Now, what can this tell us? Now, that depends on what is the relationship of this path difference with respect to the wavelength of the light or the wavelength of the incident radiation. And how does that work? So, let us briefly look at interference of waves. Now, one situation can be as follows. I have a, let us say, ray 1 this is ray 1, it has let us say an amplitude of 1. Let us consider ray 2, which also has an amplitude of 1, and as you can see that the valleys correspond to the valleys in ray 1, the peaks correspond to the peaks of the two rays 1 and 2. Such a situation we call that these two waves are in phase, and essentially the path difference is 0. If I add these two rays together, they will get amplified to an amplitude of 2. So, here what is happening is what we describe this as constructive interference. And we will get a finite intensity in this case. Now, consider another situation. So, ray 1 has an amplitude of 1 and now consider ray 2. Ray 2 in this case you can see that there is where there is a peak out here, this peak is below the line and so on. So, rather the peaks are corresponding to the valleys and the valleys are corresponding to the peak. So, peak out here corresponds to the valley here, valley out here corresponds to the peak. Similarly, this is peak, valley, valley, peak and so on. And if I now add up ray 1 and ray 2, both have the same amplitude, but however they will completely cancel out and essentially one will get complete annihilation or what we can call as destructive interference. So, out here is constructive interference, here it is destructive interference. In fact, this destructive interference is used to create such devices as noise cancellation headphones. Now, this I would call it in phase, this is out of phase. We can also, so this is out of phase and in fact it is 180 degrees out of phase. Or you can say that I have shifted ray 2 with respect to ray 1 by essentially creating a path difference of lambda upon 2. So, when I shift the wave by a distance of lambda by 2, and remember lambda is your wavelength, which is represented like this. So, this out here is lambda upon 2. So, if I shift by lambda by 2, you can clearly see that the peaks will correspond to the valleys and the valleys will correspond to the peaks. So, now coming to this, we want to find out when the path difference, what kind of a path difference should be, so that the rays are coming in phase. Now, that is possible when delta 1 2 is an integral multiple of lambda. So, if delta path difference is an integral multiple of lambda, which is constructive interference, I will get a finite intensity, and hence I can now write down. So, this is constructive interference if delta 1 2 was equal to 2n plus 1 times lambda by 2. So, I am multiplying it by an odd number times lambda by 2. This creates destructive interference. Now, there can be situation where the path difference is in between the two, constructive interference to total destructive interference could be, let us say, 90 degrees out of phase or 45 degrees out of phase. Then there is going to be partial constructive, partial destructive. Hence, I can now write, basically we have written this out here, that this actually becomes the condition for diffraction. N lambda equals d sin theta. So, this is condition for diffraction. Now, what we will do is we will conduct a small experiment on diffraction. If we look at a DVD, so DVD has tracks and the tracks have certain spacing. These tracks are nothing but, you can imagine that there are grooves on the DVD surface, and these grooves basically act as a diffraction grating. So, DVD can be used as a in fact, not just DVD, you can also use a CD. CD or a DVD can be used as a diffraction grating. If I look at a DVD surface under a microscope, we can see these tracks that are on the surface, and these tracks are very close to each other. For example, in the case of DVD, the track spacing is of the order of 740 nanometers. Now, onto this DVD, so I will take a DVD, let me just show a side view of it, and I take a laser and shoot a laser beam onto the DVD, and before that, of course, I have to remove the backing, the label part of the DVD. You have to separate the two layers and take the basically the transparent part on which the actual writing is done. This would create a diffraction pattern. This is what is the transmitted beam or the direct beam. So, this is the transmitted spot, and then I will have several diffraction spots. Now, why do I get many of them? As we go further away from the transmitted spot, the distance between the spots keep increasing. Now, where is this coming from? If I just go back to the previous case and look at the diffraction condition, essentially this diffraction condition is for n equals 1, 2 and so on. So, if I now try to examine, so the spot closest to the transmitted spot is corresponding to n is equal to 1. So, the two spots on either side, n is equal to 2 is the spots further down, and then here n is equal to 3. This is called as first order n is equal to 1, second order, third order, and so on. And essentially you are getting it, you will keep getting many spots as long as this equation n lambda equals d sin theta remains valid. Eventually you reach a value of n for which this equation can no longer be valid, because for that sin theta will have to become greater than 1. So, now let us very quickly do the experiment, and the objective of this experiment. So, what is the objective? The objective of the experiment is to get at least the first order spot and measure what is the distance of the first order spot from the transmitted beam. So, what we can do is, in fact, we can measure the distance between the two first order spots on either side of the transmitted beam, and this distance that we measure can then be divided by 2 to get me the distance between the first order spot and the transmitted beam. And what do I do with that? So, if I just again, if I come to this, I need to find out this value of theta from this experiment. In order to get the value of theta, so it is like this is my transmitted beam, this is my diffracted beam, this is transmitted, this angle is theta, that is what I want to find out. So, in order to find out, so I need the distance between the, let us say this is for n is equal to 1. So, this distance I need, let me call this distance as let us say x, let me call this distance is from the CD surface to the projection plane. So, this is my projection plane. And let me call that distance to be, let us say, capital R. Then I can write down tan theta is x upon r. Once I know r, once I know theta from here, I can directly plug it into the diffraction equation n lambda equals d sin theta and put n is equal to 1. If I know what is the wavelength of the laser that I am using and I have measured theta, I would be able to find out the value of the distance between the tracks or the track spacing on a DVD, which I have said should be of the order of 740 nanometers. So, my objective is to find track spacing on a DVD. Now, let us quickly have a look at the experiment and make these measurements, and once I have these measurements, then I can calculate what is theta, then I can put it in the diffraction condition and find out the track spacing. So, let us quickly look at the experiment. So, here is a setup I just described, which consists of a DVD laser. A DVD acts like a diffraction grating. So, if I look at this setup, this out here is my laser, it is a green laser which has a very specific wavelength. And then what we did was we took a DVD, and DVD, as you know, has two layers. One is a layer on which the actual writing is done, which contains the grooves, the tracks of a DVD. So, what we did was, this is the back part of the DVD where the label is put and essentially provides a silver backing to the transparent layer. So, these two layers were separated, and then we have this separated DVD out here through which my laser beam will pass through. So, I have once again I have a laser, a DVD, and then the projection plane at the bottom on which I have put a white sheet of paper. Now, what we do is when we switch on the laser, the laser light will get scattered by the tracks. So, you will get a diffraction pattern and you will get spots, diffraction spots where the laser rays undergo constructive interference. So, now with this let us try and turn this laser on, but also what we did was we also measured the distance of the DVD to the projection plane, which is essentially nothing but the surface of the table. So, this distance turned out to be 130 millimeters, and then now let us turn the laser on and have a look at what kind of a pattern we get. So, here what we have a direct beam. This is the transmitted spot, and out here the two on either side of the transmitted spot you have two diffraction spots. These two spots are first order spots for which n is equal to 1. Now, there are other spots also, but they are so far away that we cannot capture those spots in this experiment out here. Now, once we have these diffraction spots, I will put this ruler here and measure the distance between the pair of diffraction spots. So, first let me just draw a line through it and mark out the spots. And then once I have marked the central spot, I have marked the two diffraction spots. Now, I can make the measurements and calculate what should be the track spacing of the DVD. So, now this experiment is a very simple experiment, as you can see, and let us go back to our and do some calculations now, and let us see what kind of results we get out of this. So, let us go back and do the calculations now to look at what kind of track spacing I can get for a DVD. So, we did the experiment and we got values like this, that we measured the distance between the two diffraction spots on either side of the central spot or the transmitted spot to get the distance between the diffracted spot and the transmitted spot. And in that experiment, we had also measured the distance between the DVD and the projection plane. Using these values, we will now calculate what is the track spacing. So, I have done these following measurements. So, this is my transmitted spot, this is my two pair of diffracted spots on either side, and we had measured this distance, which is I had designated as 285 millimeters. So, again let me just draw that diagram. So, I have this is x, this is r, basically this is my DVD out here and this is my projection plane. R we had measured to be 130 millimeters. Now, using these two values, we can quickly find out what is the angle theta. So, angle theta I can write it to be tan theta equals x upon r, which is 200 x. So, x will be Now 285 millimeters is the distance between the pair of spots. So, distance between the transmitted spot and the diffracted spot would be 285 upon 2, and this would give me 142.5 millimeters. So, I can write for tan theta, I can write 142.5 divided by 130, or theta equals tan inverse 142.5 divided by 130. Now, this gives us a value of theta to be, let us try to find this out, 47.6 degrees. That is right, 47.6 degrees. Now, my diffraction condition is n lambda equals d sin theta, or I can write d to be equal to n lambda divided by sin theta, but now this is for the spot that I am getting is for n is equal to 1. So, I can write this as lambda upon sin theta, or the track spacing becomes, now I have used the green laser, and the specification of the laser says that the wavelength of that is 532 nanometers. So, I write 532 divided by sine of 47.6 degrees. So, let us calculate this. So, if we look at this, we can first take the sine of 47.6 0.738, it is in the denominator, to let us take the reciprocal of this 1 upon x. So, you get this value 1.35 multiplied by the wavelength, which is 532. This essentially gives me a value of about 720 and 720 nanometers. Now, we can compare this with the specification for a DVD, that the spacing should be around 740 nanometers. So, this is, I would say, a pretty good value, because our setup was quite crude, our measurements were also, I had used a simple ruler which has a resolution of only 1 millimeter. So, if I improve all of those measurement tools that I have, I align the laser properly, I align the DVD properly, then we would be able to get even better value than this. But then even for such a crude experiment, we get quite a good value for the DVD. So, all this experiment is trying to show is that we have, by some very simple, the experiment is trying to show that diffraction is a very powerful tool for making measurements. And in the case of crystals, we would be able to measure lattice parameters in very, very accurately. So, in terms of nanometers, one can easily go to accuracy of 4 decimal places when you have sophisticated X-ray diffraction equipment. Thank you.